All right, for example 4, it's the same exact setup here, but instead of breaking it up into 4 subintervals, partitioning our interval from 0 to 1 into 4 pieces, we want to break it up into n pieces and see what happens as the number of subintervals, that n value that's right there, approaches infinity. And in doing so, we should be able to show that the area of this region is exactly 1/3. I have evidence right here. I have numerical evidence to suggest that as I increase the number of rectangles from any one of these directions, that it seems to be getting closer to 1/3. So we're going to do that with an actual limit and proof that it is exactly 1/3. So let's start with, why not a right Riemann sum? Right Riemann sum, pretty much my favorite sum. And the reason why is because it's very easy to just use the right endpoints and plug those right into the function, as you're going to see. So for a Riemann sum, remember you need two things. You need a function value and you need a width. The width is the easier part of that thing, and the formula is b minus a over n. Our b here is 1, and our a is 0 because we're on the interval from 0 to 1, a, b, over n. Simplifies down to 1 over n. So before we had 1 over 4 because we had 4 little subintervals. Here we have n of them. Doesn't it make sense that each one is just 1 over n? So there's our width. Now we also need our height, which is a function value. So each one of our heights is going to be evaluated at, here, let me draw a picture for you. This picture is going to be fantastic. It's not going to win any awards or anything, but it'll be enough for us to be able to wrap our heads around what's going on. So here's that's y equals x squared, in case you couldn't tell. All right, and we're going to break this thing up into subintervals, and we're using the right endpoints for each one of our rectangles. So, I'd have something like this. Now, when we did this the first time, we had 1/4 and 2/4 and 3/4 and so on, right? Okay, now, instead of having 1/4 for the width of each one of these things, we said our new width is 1 over n. So the first x value that we'll have is 1 over n. Second one is going to be a 2 over n, then a 3 over n, and so on, right? And we would take those values and we would plug them into the function to find the height of each one of these little rectangles. So our heights should be f of 1 over n, f of 2 over n, f of 3 over n, and you're going to continue until you get to f of n over n, and n over n, of course, is 1, right? It's this other endpoint that's over here. Okay, so we kind of want to generalize that so that we can put it into the summation formula to actually write the summation that represents our right Riemann sum. So remember that this one comes from I equals 1. This one from I is equal to 2, I is equal to 3, you skip a few, and this one is I is equal to n. All right, can you see that if we stick in 1, we get the 1 that we need. We stick in a 2, we get the 2 that we need. The 3, we get the 3 that we need. This is why the right Riemann sum is the easier one, right? It's just evaluated right there at our I values. So here then is our right Riemann sum. It's going to be the approximation for our area. Summation from I equals 1, and instead of going to 4, we're going to go up to n because we want n subintervals. We need two things in our summation. We need a function value, which is going to be f of I over 4, right? I stick in 1 here, I get 1/4, or not 1/4, oh my god, it's not 1/4, 1 over I over n. There we go. Okay, so let's see if we can correct this. Stick a 1 here, I have 1 over n, which is that first one. I stick a 2 after I increase the counter, 2 over n, this is the next one. Increase it again, 3 over n, which is the next one, and so on. All right, and then we also need our width, and our width, we said, is 1 over n. All right, so far so good, right? Okay, now we discussed the fact that This I is the variable for the summation. Everything else is a constant, including this n. I know we're changing the value of n, but not for the summation. Since this is a constant, constants get to come out. It's going to be common to each one of the things that we summation, each one of the products basically. And we saw that in a number of these examples. Here, I've got an example for you, like right over here. See, we have it. Come on. Okay, yeah, we have it here, 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 and here. It could be factored out at the very, very beginning. We're going to do the same thing here to simplify our sum a whole bunch. And take this 1 over n, we're going to just bring it out to the front. So this is going to be equal to, just a minute, guys, I got to switch back to blue. 1 over n times the summation of f of I over n. Again, this is from I is equal to 1 up to n. Okay, now then, I'm going to just take this I over n and substitute it into my equation, which is right here. I'm just going to take I over n and then square it. So this will now be equal to 1 over n times the summation from I equals 1 to n of I over n squared. And you can, of course, square each one of those things and get I squared over n squared. Let me point out once again that I is the variable for the summation, not n. So this n squared that's in the denominator down here is still a constant number that can be factored out. And it can actually multiply times this n, which is already here, and make this 1 over n cubed times the summation from I equals 1 to n of I squared. Now, if only there was a way to sum up from I equals 1 to n of all of the squared integers. Do we have a formula for such a thing? You know what? I think we do. Here, let me go back, dial it back. It is way the heck over here. Here it is. Again, you don't have to have these things memorized. You have it written down someplace. You can just use it. So the sum from I equals 1 to n of I squared, that's the sum of the squared integers, so 1 squared, 2 squared, 3 squared, and so on, is n times n plus 1 times 2n plus 1, all of that divided by 6. Let's throw that into our summation. Actually, use that to evaluate our summation. So this will now be equal to, and for the sake of space, I'm going to cram it way the heck over here to the left, 1 over n cubed times, and this summation right here is n times n plus 1 times 2n plus 1, all of this divided by 6. That was taken from the sum formula for I squared. Now then, all I got to do is just kind of simplify this a little bit, like I could do top times top and bottom times bottom, but once you notice with your cancellation crayon that one of these factors of n cancels out. 2. All right, so the simplest form here is just going to be equal to n plus 1 times 2n plus 1 over 6n squared. So basically, you have yourself a little formula that you could use. Depending on how many rectangles that you have, you could just plug in your n value, and you can find out what the approximate Riemann sum is for that number of rectangles, or that number of subintervals. So what if we were to take that thing and take the limit as n approaches infinity? N is the number of subintervals, which corresponds to the number of rectangles. So think about this. As the number of rectangles gets closer and closer to infinity, the size of those rectangles, the width of those rectangles, is getting closer and closer to 0. And then I'm basically adding up an infinite number of those things. Okay, over 6n squared. So if you were to plug in infinity here, you'd have infinity over infinity, which means L'Hopital's rule would apply, but I don't even have to use that. I can use a pre-cal rule because the degree of the bottom is 2, and the degree of the top would also be 2 if I were to like FOIL this thing out, it would be a 2n squared. And from pre-calculus, the value of this limit, after you erase it, come on, the value of this limit is equal to the ratio of the two coefficients here, which is 2/6, otherwise known as 1/3. So there you have it. We have just showed that whenever you take the limit of the right Riemann sum, that the area underneath this curve is exactly 1/3. All right, but here's a follow-up question. We use the right Riemann sum. What would happen if we use the left Riemann sum instead of the right one? I know it's a heck of a lot more tedious to do, but let's just see what does happen when we take the left Riemann sum. Okay, so I'm going to sketch a picture of this one just like I did before. Award-winning picture here, x and y axis, and the picture of your parabola. Look how perfectly symmetric that is. Okay, lovely. All right, and we're going to break this up into subintervals thusly, but this time we're going to use the left endpoints, right? Those are like this. So the first time we did this, we started with 0, and then we had 1/4, and then we had 1/2, and so on. But now, remember that our width, delta x, is 1 minus 0, b minus a, over n, which is 1 over n, just like it was for the right Riemann sum. So instead of having 0, 1/4, 1/2, and all of that, we're still going to have 0, but this one is going to be 1 over n, and then a 2 over n, just like it was for the right Riemann sum, 3 over n, and then so on. So for our heights, we're going to find function values at each one of these left endpoints, and the first one is going to be f of 0, and then f of 1 over n, f of 2 over n, 3 over n, and you get the picture all the way up to, you don't go to n over n because that's the right endpoint, and remember with the left Riemann sum you leave it off. We're going to go to f of n minus 1 over n. That should be the last one. Okay, all right, so we kind of want to generalize this so that we can put it in the little formula, be able to take the limit of this thing. So that came from I is equal to 1, I is equal to 2, I is equal to 3. And we can think of this 0 as 0 over n. So what do you have to do to 1 to get 0? Besides erase it, okay, what do you have to do to 1 to get 0? What do you have to do to 2 to get 1? What do you have to do to 3 to get 2? Obviously, you're just going to subtract 1 from it. So our left Riemann sum can be written in summation notation like this. From I equals 1 to n, we need a function value, and that function value is going to be f of I minus 1 over n. Let's just verify this. If I stick in 1 here, stick in 1, 1 minus 1 is 0, divided by n, I get f of 0. Increase this by 1, go up to 2, 2 minus 1, 1 over n, that's our next x value, and so on. Multiplied times our width, and our width was 1 over n. So now let's evaluate this just like we did before. This is a constant because the variable for the summation is I. N is not going to change. We're just going to bring this out to the front. 1 over n times the summation, I equals 1 to n, of f of I minus 1 over n. Okay, so where are we going to get this? We'll get that by plugging I minus 1 over n into our function x squared. You're going to see very quickly that this one is not as fun as the right Riemann sum. Like if you're going to define fun, it's not the left side. Okay, all right, so I'm going to have I minus 1 over n, and you're going to square all of that stuff. So we'll have to square this business and square that business. Bring all this other stuff down. I would have, so think of the square of a binomial. That's going to be I squared minus 2I plus 1 whenever you square out this I minus 1 across the top over n squared. Once again, the n right here is basically a constant in terms of the variable for this summation. So it gets to come out and meet this other n to make 1 over n cubed, summation from I equals 1 to n, of I squared minus 2I plus 1. Now we have another property of summations, and it was the one that was sort of like this. The sum of a sum or a difference is the sum or difference of the sums. So what we're going to do is we're going to just basically break this up into a whole bunch of different pieces like this. It's going to be a mess at first. Just work with me here. N cubed. I'm going to have big O brackets, summation, and I'm getting sick of writing from 1 to n, so I'm just going to leave it like that. I squared minus summation 2I plus summation of 1. As a matter of fact, this 2I that's right here, I'm not even going to put the 2 inside of there. Instead, since it's a constant, it's going to come out. There we go. Now, if you will recall, we have already done the summation of I squared. It was this thing that was right here. So we're just going to copy that thing down, as well as the rest of it. 1 over n cubed, and I have n times n plus 1, 2n plus 1. Don't have to have it memorized, don't worry. The only reason why I can rattle that off is because I have it written right beside me. Anyway, minus 2 times, and now the summation from I of just the integers, that's the Euler one, which is n times n plus 1. Did I say Euler? I meant Gauss, yeah, over 2. And then, hey, what's the sum of n ones? It's 1 plus 1 plus 1 plus 1 plus 1 n times. That's just n. Again, you have a formula for that. Look it up. All right, then. Now what I'm going to do is I'm just going to take this 1 over n cubed and distribute it through the brackets. And as we saw before, one of these factors of n will cancel out with one of the factors of n cubed down at the bottom, and I would have n plus 1 times 2n plus 1 over 6n squared. These 2's, they cancel out, don't they? And then I'm just going to still have this n cubed on the bottom over here. So n times n plus 1 over n cubed. And if you want to, you can reduce that by a factor of n as well. So get rid of this n, get rid of this 3, and turn it into a 2. Plus, take this 1 over n cubed and multiply it times n. Of course, you're going to have n over n cubed. You can reduce those by a factor of n, like that 1 over n squared. All right, so far, fantastic. Now what do? We take the limit of all this. Limit as n approaches infinity. There's no way that this is going to turn out to be the same thing as it was before. No way at all. So I'm just going to duplicate that because I don't want to write it down again. Okay. Well, we already know the limit as n goes to infinity of this quantity, because that's essentially the same thing that we got for the right Riemann sum. That's 1/3. Okay, but we still have these other things that we have to subtract and add from it. If I take the limit as n goes to infinity of this, n plus 1 over n squared, what do you get there? 0. Why is that? Because this is n and this is n squared. This is increasing faster than the top. That's going to go to 0. Likewise, this one over here is also going to go to 0. And we can obviously see the zeros cancel out, right? A negative 0 and a positive 0, they cancel out. And once again, we can see that that sum converges to 1/3. We're getting closer and closer to 1/3 as we increase the number of rectangles, which in turn decreases the size of the rectangles. So it doesn't matter if I approach it from the left side or I approach it from the right side, I'm still going to get the exact same area. In which case, choose the one that's going to be easier. And which one is going to be easier? we demonstrated very clearly that that's going to be the right Riemann sum. So in the next video, we're going to tie this thing together to finally define the area of a plane region.